Today we will talk about the factor model for large dimensional time series. In the modern information age, analysis of large data set is an integral part of scientific research as well as practical problem solving. In particular, high-dimensional time series is a commonplace in many fields, including finance, economics, environmental, and medical studies. For example, understanding the dynamics of the return of large number of assets is a key to asset pricing and risk management. And the environmental study is often of a high dimension because of large number of indices monitored across many different locations. However, the standard multiple time series models such as vector AR model and vector ARMA model is not particularly useful when dimension p is large, since the parameter involved is of order p square. There are too many parameters needs to be estimated. Modeling by the common factors is one of the frequently used methods to achieve the dimension reduction in analyzing the multiple time series. Other methods include the principal component analysis, clinical correlation analysis, and reduced rank regression. These four methods are a technique to do the dimension reduction for the multiple time series. Basically, there are three groups of researchers use the factor analysis to model the high-dimensional time series. Professor Jun Shanbai from the Columbia University, they applies the principal component estimator, and Frony and some researchers from Europe, they use the dynamic principal component method. We will focus on the Professor Yao's method. Professor Yao adopt a different and more statistical approach in their paper to achieve the dimension reduction. They decompose the p-dimensional time series into two parts. The dynamic part, driven by the low-dimensional factor process, and the static part, which is a vector of white noise. This xt is the low-dimensional factor process, and this epsilon t is white noise. And we assume xt is strictly stationary with finite first two moments. And this A is called constant factor loading, which is shared among all time t. Epsilon t is white noise with mean 0 and variance sigma epsilon. The problem for the factor model is that we only observe the yt at n time points. Both factor loading A and low-dimensional factor process are unobserved. We need to estimate both A and xt. The issue for this factor model is identifiability. That is, for any invertible matrix H, we have the following equation, which means that AH and H inverse XT is still satisfy our model. Thus, A is not unique. Only the linear space of A is unique. Further, in the later, we will see that the non-uniqueness of A is an advantage for our estimation. We can see this point later. The key assumption in the paper is related to the strength of the factor, which assume that the norm of each column of factor loading A is of order p power 1 minus delta. Let's rewrite the A as a column vector format. The important point in this paper is that the R is assumed to be known and is fixed and less or equal to P. The first assumption is that column norm is of order P power 1 minus delta. When the delta equal to 0, we have the factor called strong factor. The rate of convergence, we will see later, in this case is independent of dimension P. When delta is lying 0 and 1, we state that the factor is a weak factor. Also, we assume that all R factor A1 to AR are of equal strength, which is given by the following assumption. This assumptions means that any column in A cannot be replaced by other columns. It kind of approximates orthogonal. First, we can rewrite the factor model using the QR decomposition. You apply the QR decomposition to A. A is a matrix of P by R. The QR decomposition gives part of a unitary matrix. This Q is P by R, and this upper triangle matrix is R by R. For this Q, it is satisfied that the Q transpose Q equal to the identity. So we can rewrite our model and treat this R xt as a new variable. We can call it ft. Ft is still a low-dimensional factor process. However, Even though we transform this problem in this way, the matrix Q is still not unique because of the unitary transformation. For any R by R a unitary matrix, which means its inverse is its transpose. We have the Q, U, and U transpose FT still satisfy our model. Next, I will introduce some notation and state the assumptions in the paper, as well as the estimation method. For each lag k, we define the sample version of autocurrence. Sigma autocurrence matrix of X at lag k, the sample version is given by typo. We can define the sample version of autocovariance for Ft in similar way, also for Y in similar way. We can also define the autocovariance between Ft and white noise in the following way. Typo. Also, we can exchange the order of epsilon and f. Which gives a sample version of the autocurrence between the white noise and the low dimensional process. For assumption part, first assumption is about the low dimensional process xt. No linear combination of the xt elements of xt is white noise. Otherwise, it can be absorbed into the epsilon t, which is the white noise part. Second assumption is about the autocurrence. For k equal to 1 to k0, this k0 is a small positive integer which can be 1, 3, or 5. The value of the k0 does not affect the further result, which is given by the simulation in the original paper. The assumption is that the autocurrence at lag k for x is full rank, which is a stronger assumption than assumption A, since the assumption A can imply that there exists at least one k bigger than 0 for which the autocurrence at that lag k is full ranked. And assumption B tells us that the k can be any number in 1, 2, 3, 4 to k0. Assumption C is that element of autocurrence and covariance matrix for white noise the elements of these two matrices is of order O1. Even when P increase, these two covariants behave normally. The first assumption is classical, which tells us the correlation between epsilon s and xt is 0 for s less than t. It means that the past information cannot depend on the future information, which is very natural. Assumption E is that yt is strictly stationary. And the first moment for yt is finite. Next, we can see how the non-uniqueness of A or Q provides the flexibility for our estimation. For any k greater or equal to 1, autocovariance of y at lag k equals plug in our model assumption here we use assumption D, which means that autocurrence at lag k for white noise and F is 0. Future cannot contribute to the past. Because there are some cancellation for different lags if we add them together. In order to keep the information for different lags, we can square them. To make all lag information positive. For matrix language, that is to make a positive semi-definite matrix. If we do in this way, then this matrix is positive semi-definite. And we further define the matrix L, which is given by this matrix L is also positive semi-definite and symmetric, which can provide some advantage for our estimation. Let's expand the definition of L. The second term is same as the first term. I do not copy. Note that the middle term is complex. If it can be a diagonal matrix, then our analysis will become easier. The middle term is also equal to Q transpose LQ, since Q transpose Q equal to identity. We can multiply the Q transpose and Q on both sides of L. Because this middle term Q transpose LQ is a positive semi-definite, then there is a theorem tell us that for positive semi-definite matrix, the eigenvalue decomposition or singular value decomposition are same. Let's do the eigenvalue decomposition. This D is diagonal matrix, and U is orthogonal matrix or unitary matrix. So we can have L equal to this. And notice that this QU is satisfying our model. That is to say, we rotate the ft in a special way by ut, because any unitary matrix is rotation matrix. We can call it ft prime. Let's rewrite our model. This Q is from QR decomposition. This U is from eigenvalue decomposition. And we combine them. We can get we can take this QU as new Q. Now, the middle term is diagonal matrix. Which is the convenience brought by the non-uniqueness of A or U. That is to say, Q is a special matrix, why we have this double code? Because the Q is P by R. We only have Q transpose Q equal to identity. So it's part of unitary matrix such that the following analysis is all based on this Q, such that the Q transpose LQ is diagonal matrix. Next, we see how to estimate this Q. Because we only observe YT, so we can form the sample version of L. First, we form the sample version of autocurrence for Y and take L sample version of L as then we can perform eigenvalue decomposition of Y tutor. this Q tilde is orthogonal matrix, which is given by Q column vector, and our estimator for Q is we stock at R's column, and the estimator for xt is also we can have the residual, which is the difference between the true value and the fitted value. Moreover, if we want to do the prediction, we can first predict the f at t plus 1 time point by fitting another time series model on f hat t for t from 1 to n. Then we first estimate f hat at time point n plus 1, then the value of y is given by this. Above estimation method is very simple. Let's say the theoretical property of those estimator. Let's introduce some notation first. These two kappa min and kappa max, is used to measure the magnitude of the cross correlation between the low dimensional process F and the white noise. This notation means this is easy, which is operator norm, or to say change this min to this max. Let's give our first theorem. Let above assumption holds and eigenvalue of L lambda 1 to lambda r are different. And further, we assume p delta over square root n converge to 0, which is little o1. Then we have first the error bound is given by p delta over square root n if the magnitude of the cross correlation between low dimension process and white noise is small, which is little o of the factor strings. Remember that this p power 1 minus delta is factor strings. This rate of convergence tells us that if the factor is strong, which means delta equal to 0, the rate of convergence is independent of dimension p. We call this blessing of dimensionality, which cancels the curse of dimensionality. For delta greater than 0, the stronger the factor, the faster the rate. The second bound tells us another story, which is a scenario that the cross correlation between the low dimensional process F and the white noise epsilon is big. The error bound in this case is given by following, which related to the kappa min and the kappa max. The factor strings under this scenario is of little o of the minimal magnitude of the cross correlation. And in order for rate of convergence go to 0, we need to assume this rate is little o1. There is another remark that generally for dimension reduction method, we are interested in bounding the eigenspace, which is given by Q times Q transpose minus the population version. The difference between two linear space. But in our case, we give the bound directly to the parameter Q in L2 norm, because we assume the R eigenvalue are distinct. Otherwise, we need to bound in the format of difference between two eigenspace. Let's prove the first theorem. We have the following. where D is given by let B be the orthogonal complement of Q. We use this notation as orthogonal complement. Then Q transpose B is 0, which means LB is also 0, because L is equal to QD Q transpose. We can write in the following way: block matrix format. In the literature, we call the minimal eigenvalue of D as the eigengap, which tells us the distance between two spaces. We can also use this separation notation. This gap guarantees the successful recovery in dimension reduction problem. For example, in the principal component analysis, in the final step, we apply the Davis-Cohen theorem, or we also call sin theta theorem. In this theorem, we need the eigengap, which show in the denominator of the rate of convergence, which means this eigengap is negatively correlated with the rate of convergence. If the gap is big, then the rate of convergence is fast. Eigengap is small, which means the eigenspace are mixed. It's very hard to separate. It's very hard to estimate. For our problem, we cannot apply the Davis-Cohen theorem, because Davis-Cohen theorem is for the perturbation of the eigenspace, which is this case. But for our case, we directly bound the parameter in L2 norm, so we need another assumption. Let's introduce this lemma, which also show in the book called Matrix Computation, very useful book. You can find it in the chapter 8. Let's state it directly without proof. Suppose A and perturbed version are symmetric. This E is perturbation error, symmetric perturbation error. And Q is orthogonal matrix, which we write as a column of two matrix. This first one is n by r, and second is n by n minus r. Such that the span of Q1 is invariant subspace for A. Which means the inner product of A of span of Q1 is always belong to the Q1. We can understand this in another way. Suppose we do the eigenvalue decomposition to matrix A, and we get an orthogonal matrix Q, and we take the first R column as Q1, which satisfies this property. And we let Q transpose AQ equal to block diagonal matrix. Also for error. We have following. If the suppression for D1, D2 is greater than 0, and the perturbation error is less than the suppression over 5. Then there exists a matrix P in R with P operator norm less or equal to a number which negatively correlated with suppression and positively correlated with error, such that Q span of Q1 hat is invariant subspace for the A plus E for perturbed matrix A, where this Q1 hat is given by the formula. This is the lemma 1. In summary, this lemma tells us that if we can bound the perturbation error, then we can find the invariant subspace for the perturbed version of matrix A. In order to use this lemma 1, we need the column. The error is L tilde minus the population order. And separation of D1, D2 in our case is just not the mean, because D2 is 0, D1 equal to D. Let's find the perturbation error first. We subtract an intermediate term and add it back. So apply the triangle inequality. We have for this term, we also apply the triangle inequality and a similar trick. So we can get we can modify it. Yeah, square and should be a 2. Furthermore, we can see that this term as we shown before, it equal to the operator norm apply the triangle inequality Here, we use the unitary invariant property of the orthogonal matrix. And for second term, is less or equal to kappa max by our definition. For first term, we can see its bound later. Also, we need to bound this term. Let's expand it. We first expand the sample version. Plug in our model. For population version, we already shown that it's equal to actually we can add one more term, which is 0 Q transpose. The reason is that this is equal to 0 because the future does not contribute to the past. So this bound apply the triangle inequality. Up to now, we know we need to bound for the following term in order to give the bound for the perturbation error. Let's do a short summary. We need the bound for, I do not write this for convenience. Let's show the bound for this kind of things in following lemma. This lemma is about a bound for population version of autocurrence for F, and also the bound for autocurrence between the F and the white noise. First bound is this equivalent notation means that if A equivalent to B, then A equal to big OB and B equal to big OA. Okay, let's show these two lemma first. For one, since we know that this term is automatically lower than this term, so it remains to show that and if we can show these two, then we can get 1. Since by our assumption, the factor strings is of order p power 1 minus delta, and by QR decomposition, where A is P by R, Q is also P by R, and R, the upper triangular matrix, is R by R. Since Q is part of unitary matrix, by unitary invariant property for the unitary matrix, we have because 2 norm is unitary invariant. Let's look at the operator norm first. This 2-step adjusts the definition of operator norm as well as the matrix calculation. Since there are some cross-product term and we apply the Cauchy-Schwarz inequality, we get this inequality sign. And furthermore, we apply the inequality 2ab less or equal to a squared plus b squared. We can have this long term is less or equal to some constant which depends on r times p power 1 minus delta, which we use the assumption of the factor strings. So we have shown that operating norm of A is big O Next, we show the minimal singular value. Suppose the minimal is attained at some point. We assume this point is U star. Because this U star is r-dimensional, so one of the entry of the U star must greater or equal to 1 over r. So we have we call that entry entry I. Which is bigger than 1 over r squared. For this, we use the assumption about the all factor are of equal strengths. Let's write down that assumption explicitly. Which we have mentioned it in very earlier part. So since r is a fixed number, we have shown that is big O of up to now, we got the following result. And we can replace the A by upper triangular matrix R because of unitary invariant property of Q. Also, we have assumed that xt is strictly stationary with finite first and second moment. So we can treat the elements for autocovariance for x is of order 1. Then apply the similar argument, we can arrive that the operator norm and the minimal singular value is of order 1. Then we combine these two bonds. We can get here, this inequality, we have used the fact that for any square matrix, this can be proved by the definition of the minimal singular value, which is an easier exercise. The first bound gives us the direction of and we also have a second bound. By matrix submultiplicity, we arrive at the second. Now we have shown that the first part of lemma 2 holds. Then we try to show the second part. Notice that we use operator norm here, but the operator norm is less equal to the Frobenius norm. So for this inequality, we can change the operator norm to Frobenius norm. Then the first part we have shown in the part 1 is of this rate. And the second part is of square root p times r. Why we have this rate? because in assumption we have assumed the elements is of order 1. Since this matrix is P by R, then by the definition of Frobenius norm, we know this quantity is of P by R, P times R times 1, and take a square root. I need to clarify a point here. In the previous assumption part, I made a mistake. Here, it should be the autocurrence between the X and the white noise is O1. Sorry about that. Let's continue. Then we got the rate we want. The lemma 2 is about the population version, and the lemma 3, which gives the rate of convergence for sample version minus the population version. We have the following result. Let's prove this 5 rate of convergence. First, let's show this simple rate. Because ft equal to upper triangular matrix times xt. Since xt is strictly stationary with finite second moment, so for each entry of xt, it is big OP1, since the variance and the mean are all finite. Consequently, because R here is a fixed constant. we have shown the last rate. Let's continue. Here we apply the similar idea before. Notice that this matrix is dimension r by r for each entry, because we assume the first moment of yt is finite, and we can have the first moment of xt is also finite. Then apply the standard biometric rate, which is similar to this one. We know that for each entry, we have rate of convergence 1 over n, and we have r square total numbers of entry. So we got this rate. Combine these two big O notation, we got in this page, we show the fifth one and first one. Let's continue our proof. For white noise part, we directly use the bound that operator norm is less or equal to the Frobenius norm. Then, similar argument give us the rate p over square root n. Actually, except the last rate. The other 4 rates all apply the similar trick. First, we upper bound it by Fubini's norm, and then we analyze the entry by entry. It can be seen easily that these two share the same rate of convergence. Now, since we have obtained the bound for this kind of things, we can go back to our original problem. The bound for difference between the L and its sample word. Recall that this difference is bounded by this term. For this one, apply the lemma 2 and definition of kappa max we have. For this term, previously we have expanded in following way. The right hand side can be written as the summation of many differences. Then we plug in the rate from lemma 3 to this inequality. We got it remain to got the rate of this one. By the standard added and subtraction trick, we have